Have you ever wondered why a compass needle always points north? Earth acts like a giant bar magnet, creating a complex magnetic field that protects our planet and guides our navigation across the globe. Crucially, the Earth's magnetic poles do not align perfectly with its geographic poles. The magnetic axis is tilted at approximately 11.5 degrees relative to the axis of rotation, creating a distinction between true north and magnetic north. To precisely define the Earth's magnetic field at any specific location, we use three parameters known as the magnetic elements: declination, inclination, and the horizontal component of the magnetic field. Magnetic inclination, or dip, is the angle that the total magnetic field vector makes with the horizontal surface of the Earth. It represents the vertical tilt of the magnetic field lines. At the magnetic equator, the magnetic field lines are perfectly parallel to the Earth's surface. Therefore, the angle of dip is 0 degrees, and a dip needle remains perfectly horizontal. As you move toward the magnetic poles, the field lines become steeper. At the magnetic poles, the field lines are perpendicular to the surface, resulting in a dip angle of 90 degrees. The horizontal component, BH, is the part of the magnetic field that acts along the Earth's surface. It is calculated as the total field strength multiplied by the cosine of the dip angle. Conversely, the vertical component, BV, represents the field strength acting perpendicular to the surface. It is determined by the total field strength multiplied by the sine of the dip angle. By dividing the vertical component by the horizontal component, we find that the tangent of the dip angle is equal to the ratio of BV to BH. This is a fundamental relationship in geomagnetism. Let's try an example. If the total magnetic field at a point is 0 for Gauss and the dip angle is 60 degrees, we find BH by multiplying 0.4 by 0.5, resulting in 0.2 Gauss. In a case where the horizontal and vertical components are equal, the tangent of the dip angle is 1. This means the magnetic dip at that specific location is exactly 45 degrees. Scientists use magnetic maps to visualize these elements. Isogarnic lines connect points with equal declination, while the aclinic line connects points where the magnetic dip is 0, marking the magnetic equator. To summarize, the Earth's magnetic field is defined by declination, inclination, and the horizontal component. Together, these elements allow us to map the invisible forces surrounding our planet. Time for a quick check. Based on what we learned about the angle of dip, at which location would the horizontal component of the magnetic field be 0? Think about the pole vs the equator. The answer is the magnetic poles. Since the dip angle at the poles is 90 degrees, and the cosine of 90 is 0, the horizontal component vanishes. Thank you for learning with us. Generated by Vision Solve AI.